So this is going to be a quick run through of what we talked about again on Thursday in terms of finding or evaluating the integral. The big question we're going to address in this video is going to be that how is net area a function? So that's what we got to keep in mind as we move forward. So the function that we're looking at is f of x, and this function is drawn here. So we're just going to label it f of x so we know. The other thing to keep in mind, we're just going from -4 to 5. That's where it exists, okay? And it says to use complete sentences to explain the geometrical meaning of the integral from 0 to x of f of t dt. Well, just a quick review again of what we did Thursday. 0 is your starting point. So everything we color, all the area, the net area, is going to start at 0. So this is sort of our starting point. X represents the place where we're going to stop, the direction where we're going to go. And the reason we're using t is to not double dip on using that same variable twice. But really, we're still talking about the function f of x, okay? And so as we start at 0 and we start to color, whether we go to the right, keep in mind if we go to the right, we're going to get a positive area. So all of this area would have been positive. Sorry, it's kind of hard to draw, but all of this area again, positive, positive. But if we move to the left, because we are above the x-axis, but moving to the left, then of course this area is going to be negative. And something kind of interesting, when you go below, again, but since we're moving to the left, again, we started at 0, we're moving to the left, this area here is actually going to be positive again, okay? So you can see that positive. Moving to the right causes positive area. Moving to the left causes negative. But then when we end up below the x-axis, that becomes positive again. So what does this mean? Well, this means the net area starting at 0 under the function f of x, stopping at some point x. And I'm not going to write all that down because it's really hard to write with this pen. But again, it's the net area starting at 0 under the function f of x, all the way into some point x, and that's going to change depending on what they want us to find. Okay, so let's actually work out the examples that we did Thursday. And if you were there Thursday and you got this, then you're fine. If you were not there Thursday, then this would be good for you. And if you were there but you're still confused, this is sort of a review. So we're going to let g of x be the integral from 0 to x of f of t dt. Remember, here's f of x. F of t is simply f of x. We're just using t, so we don't use x twice. And they want us to evaluate the following. So first of all, they want us to find g of 0. Well, there was a property that you copied in your notes, and it kind of makes sense. G of 0 would simply mean the integral from 0. We're going to plug our 0 in for x. That's right there. So we're going to have from 0 to 0 of, and I can use x again because I no longer have x up at the top boundary. And we studied a property, or you wrote down a property that said basically we're not moving. We're just at 0. There's no area if you don't move. So the answer to that one is 0. G of 3 is going to be the same thing. We're going to take the net area from 0, but this time we're going to move over to 3 of the function f of x dx. So what that means is start at 0, right here, but you need to move to the right all the way to 3. And you need to calculate the area under the curve. I call it curve. Of course it's line, but it could be a curve. Or under the function f of x. This case is going to be a trapezoid. And we already know that that area is going to be positive. And so I can use my formula for trapezoids, 1/2 the height and times the sum of the bases. And if I use that and compute it, I'm going to get an answer of positive 5. The height, of course, would have been 2. The bases would have been 2 and 3. It's going to give me 5. Again, positive. G of 5. All right, well, G of 5 says start at 0, and instead of going to 3, just keep going all the way to 5. So that's going to be the integral from 0 to 5 of the function under the function f of x dx. Well, what's cool about this, we already have the first trapezoid. We found that. And area is cumulative. So you start again from 0. We already know this is 3. sorry, that's not 3, that's 5. It's this answer right here, 5. And we're going to go 2 more units all the way to 5, which means this creates a triangle. We're going to add that triangle. Again, area above the x-axis to the right is positive. So 1/2 base times height is going to reveal that this is 3. So I get the area 5 plus 3. One more time, I'm using 1/2 base times height geometry formulas to compute these areas. And my total is 8. Because g of 5 is the area starting at 0 all the way to 5. Next one says g of -3. So this time we're going to start at 0, but instead of moving right, we got to go left. F of x dx. So we had talked about that earlier. We said, hey, if we start at 0 and go left, that's going to create negative area because we're above the x-axis to the left. It is a trapezoid, so we're going to do 1/2 the base times, 1/2 the height times the sum of the bases. And when you do that, the area comes out to 4, but we know it's negative because we're moving to the left above the x-axis. Okay? Last one says to go from 0 all the way to -4. Again, we already know what the value all the way to -3 is, so we'll keep in mind that that's -4. But remember that now I'm below moving to the left, which causes that area to be positive. So this itty bitty triangle here is going to have a positive area. I'm putting in blue to show that it's positive. And 1/2 base times height looks like the base is 1, the height is 1. So this is going to be a positive 1/2. So when I combine from 0 to -4, I have a -4 plus 1/2 gives me -3.5. So that's how you compute these. It's very important that you note where to start. I didn't do it in this one. Let's see, it was the integral from 0. That's what the function is defined as. And it goes to -4 of the area under the function f of x dx. You don't always start at 0, so this guy will switch up depending on what they define the function to be. And it's just important to keep in mind that that's your starting point. It's not negotiable, it's what they give you. And then this changes, and as the top boundary changes, so does your answer for the net area. The last section is going to remind us a little bit of the max and min section that we just completed. And you'll notice it asks you, where does the max value for g of x occur? The max value for g of x occurs, well, we're going to think of this just kind of by looking at the picture. If we start at 0 and we move to the right, we get positive area. And if we move to the left, we get negative area. And even if this little guy becomes positive in the end, it's still not a whole lot of positive area. So we actually found that to be -3.5 when you cancel the positive with the negative. So that's definitely not the highest value of the function g of x, which is supposed to represent the net area under the curve starting at 0. So what makes sense as our max value? Well, I would go with 8. I would go with, if we color to the right all the way to 5, that seems to be the place where we're going to get the most positive area. So where, and this is a typo, where does the max value of g of x occur? Well, I think it occurs when x is 5. And what is that max value? Well, that max value is going to be 8. Min, where does the min value of g of x occur? Again, if we're moving to the right, we're going to get positive. So it's not going to be the min positive, because we know that if we move to the left, we can get negatives. Now, the most negative area that I get is going to be here at -3, because after that, I'm actually adding positive area, which means my value is going to get bigger, not smaller. So I would say that my min value occurs at x equals -3, and that min value, of course, is going to be -4. And for this function, remember, only exists from -4 to 5, so these make sense for us. And that's it. This is how you evaluate integrals using areas. Later on, we're going to talk about algebraically, but right now, this is how you would do it using areas. So I'll go ahead and let you complete the next section in your worksheet, and I'll press pause.